Hello everybody, welcome to the first video of the playlist of computational thinking for IGCSE. Okay, so in this chapter or in this video we are going to discuss about computational thinking. We are going to introduce decomposition and abstraction. So let's see what computational thinking is. Computational thinking is a human process for machine solution. Okay, it's not how machine think. It is just simply a human process for machine solutions. Computational thinking simply is the thought process involved in formulating problems and their solutions so that the solutions can be effectively carried out by a computer. So simply it is the thought process that will result in solutions that can be used by computers. Okay, so it's itself is not the computer thinking or how computers think. This is just simply how human need to think to just create solutions that can be done or that can be executed by computers. So computers are mindless machines that only do exactly what they are told. Computational thinking is the human skill of defining the exact instructions a computer need to solve a problem. Okay, so that is what computational thinking is. So overall, okay, computational thinking is not about thinking like a machine. It is focused on creating a structured algorithm. Algorithm is a step-by-step instruction to solve a problem. Okay, so it is focused on creating algorithms. And it involves defining, analyzing, and structuring, okay, the solution for the computer. In computational thinking, there are two very important concepts, okay, that we have to understand. The first one is decomposition, and the second one is abstraction. Decomposition simply means breaking the problem down, okay. It is taking a massive complex problem or system and dividing it into smaller manageable subproblems. Okay, so we'll just discuss more about them. And abstraction is removing the noise, hiding or stripping away unnecessary details so that only the essential features remain. Okay, so hiding or stripping away the unnecessary detail to focus on the necessary ones. Now see, decomposition is kind of a divide and conquer thing. Okay, you just break a problem down into smaller manageable parts which are then easier to solve. Okay, the big problem altogether is a little bit difficult to solve. Then simply what we will divide into many smaller problems. Then those smaller problems can be solved easily. Okay, then decomposition has gotten some advantages or benefits. Okay, the first one is parallel work. Different people or different teams can tackle different subproblems in the at the exact same time. It means different people or different members of the team can work on different parts of the problem at the same time. The second one is simplified debugging. Smaller algorithms make it really easier to spot and correct errors. Okay, so that is just the second one. And reusability. Once a subproblem is coded, then that code can be saved and reused in the future programs for as many times as you want. Okay, so there are some benefits of decomposition. See a case study or an example. Okay, if we simply want to create a game of noughts and crosses, so overall the complete game or the complete problem can be divided into many problems. Okay, so here for example we have gotten the first one, design the interface. Okay, so that is this the first one, designing the visual interface or showing simply the 3x3 grid. That is just one part of the problem. Then tracking squares, keep track of which squares are selected, okay, and which one are free. So that is just another part of the problem, subproblem. Okay, then AI logic, simply determine the rules for how the computer decides which square to select next when it is just simply turn of the computer. So computer has to logically think which square should I just select next. Okay, so you have to just design that. That can be just another subproblem here. And game state, evaluate the board to decide when the game is over and who has won. Okay, so that is just an example of decomposing a noughts and crosses game. Then inside decomposition, we have to just study the structure diagram, or the other name for that is decomposition diagram. Okay, So what is a structure diagram or decomposition diagram? That is a visual tool representing decomposition results in a hierarchical view. So as you can see here, okay, create a knot and crosses game. That is just the main problem. Then we just divide it into sub problems. Okay, design of interface, keep track of squares, computer logic, and decide game state. And we will just simply keep decomposing, okay, till we just get to very simple or easy problems to solve. Okay, so for example, decide game state is further divided into two sub problems. Okay, check if all squares are used, which is draw, or check if 3 in a row match. Okay, so that is just win. So this is just an example for a structured diagram. See, in decomposition diagram or a structured diagram, we have just gotten hierarchical layout. It means main problem at the top, then sub problems just below that. Okay, specific sub problems below, and independent models. Each box represents a task that can be solved separately. Then so when designing any solution for any kind of problem, you have to just kind of determine the task requirements, and three very important things are there. Okay, three very important parts are there: inputs, processes, and outputs. You have to think what inputs does the problem need from the user, what processes or what things does it need to do, and what information does it simply need to show the user. Okay, so in our game example, the inputs are, for example, the user clicks start game and the user selects an empty square. Okay, so they are just the inputs the problem or the game receives from the user. Then the processing, okay, what things does it need to do? For example, set up the grid with 9 empty squares. Then update variables to record a player's move and check if the user has won. And the next one is display a message indicating whose turn it is. Okay, so computer's turn or player's turn, something like that. And display a final game over or winner screen. Okay, so that is just the output it needs. So for every problem, yeah, you need to just kind of determine these requirements. Okay, so after that, yeah, we are just going to talk about abstraction. Okay, what is abstraction? We just said that, yeah, the process of removing or hiding unnecessary detail so that only important points remain. Okay, so simply that is finding the signal in the noise. And we abstract the basic properties of the problem and represent them in a way computer is able to process. Okay, so for that is just an example. For example, image of a cat. So we have to just kind of take only the important parts from that to give to the computer. Okay, so that is just the abstract model. So that is abstract object type is cat. It has gotten 4 legs. It has gotten just a tail or just some characteristics of the face. So something like that. Okay, so that is an example for abstraction. And real world abstraction, again, just another example is the simulator. Okay, when you simply want to simulate things. Okay, for example, if you want to simulate any flight simulator. Okay, so that is what must be modeled, which are just really important. Okay, aerodynamics and gravity vectors, just that affects how the plane flies, for example. Then engine thrust and fuel consumption rate, then altitude, wind speed, and weather conditions. Okay, simply which affect the flight. So they are just important for this. And what things should be just kind of ignored, okay, or the unnecessary details. For example, the fabric color of the passenger seat, that is just not very important. Okay, and the smell of the cabin for this simulation, that is not very important. Okay, the brand of coffee served in the galley. Okay, so they are just not so important. That is another example of abstraction. Then another example, okay, designing the abstract model. For example, in reality, when you want to roll a dice, okay, simply rolling a dice involves calculating mass, surface friction, gravity, velocity, and angle of impact. So they are all important. Okay, but when we just simply code that, we just do not code the physical properties of bouncing plastic. We abstract the essential features, which is just simply generating a random outcome with a 1 up to 6, okay, and simply 1 in 6 probability, and represent it as a single mathematical routine. Okay, so that is just another example for abstraction. Then we're just talking about levels of abstraction in code. Okay, when you're just writing your code, how is abstraction applied there? First of all, okay, high level languages like Python, Java, C Sharp, or anything, okay, they have gotten a very high level of abstraction. Okay, they are closer to natural human language, and the programmer is completely removed from managing hardware details. Okay, so they are just hidden from the programmer, and simply easiest to write and debug. That is abstraction. Okay, and how the hardware works, how the code is just changed to machine language, they are just hidden from you. Okay, so just translator or compiler or interpreter at the middle, simply that is a necessary software that converts abstract human logic into machine readable instructions. Now then, low level or machine code, which just does not have any kind of abstraction. Okay, so that is a direct stream of ones and zeros, no abstraction, dictates the exact firing of transistors on the CPU hardware. Okay, so that is completely hidden from us when we are just coding in Python, Java, or C Sharp, or just any other high level language. Okay, so a high level of abstraction is done even on the programming languages that you are using. Okay, just think about if you needed to code everything in zeros and ones. Okay, so that would be very difficult. And the power of subprograms. Okay, subprograms are just blocks of code that performs any specific task. Okay, in programming we just do that. Okay, and practically when we want to just work on decomposition and abstraction, we use subprograms. Okay, so decomposition in action, subprograms, functions, and procedures allow us to break a massive program into self-contained testable block of code. Okay, and how just if does abstraction, simply once the code is written, the subprogram becomes like a black box. A programmer can just call its name without ever needing to look at or understand the complex logic hidden inside it. Okay, so see, there are many predefined subprograms written in any language for many complicated actions or performances. Okay, and you as a programmer simply need to just call the function, and how does it do that action that is just completely hidden from us. And when you create subprograms, you just do exactly the same thing. Then the computational pipeline. Okay, how when we are just kind of designing subprograms, what do we do? Okay, so the first one, that is the real world problem, that is messy, complex, and human centric issues. Okay, and it has just gotten a lot of extra information, big problems there. Okay, so the things that we need to do. Okay, first of all, we need to do the abstraction. Okay, simply the filter. We have to identify the essential data and strip away the irrelevant noise, or just the information which are not really necessary or needed for the solution we want to just create. Okay, so we have to just do that first. Then after that, yeah, we have to decompose. Okay, when we just get the abstracted model, then we have to just break that into distinct solvable logic puzzles. Okay, so we have to divide that into some sub problems. Then after that, yeah, we have to just design the algorithm. We have to just create or write step-by-step instructions using structured subprograms. Okay, simply writing those algorithms, how to solve each one of these subproblems that were created in decomposition level. So we will just simply write algorithms for them. Okay, then after that, yeah, we have gotten just automated solution. We will just deploy, or we will just code the algorithms that we have created. Okay, to work infinitely and efficiently. Okay, so that is just the computational pipeline, how you just perform things when you want to create softwares, or when you want to create programs that solve problems in computer. Then we have just gotten some tips for the exam. Okay, so the most important is master the terminologies. Okay, in exams, for example, they'll tell you define, or just tell us the purpose of something. So you have to know the difference between them. Okay, definition simply means what a term means or what it is. Then the purpose is why that technique is used, or why that term is used. Okay, so that is something you have to know. Then mind the scenario. Always read the scenario carefully in the exam. Okay, if the question gives you specific variable or data structures, like a list or names of variables, okay, you have to use exactly the same things in your answer. Even just the capitalization has not to change, okay. If name of a variable starts with capital letter, then yeah, you have to just start that with capital letter, okay. So you have to be very careful for that, otherwise you will lose numbers, okay. And avoid vague logic when you're just creating solutions or algorithms, okay. For example, wait for the water to heat, that is just kind of ambiguous, okay, that is not very clear. But loop until temperature is equal to 100, that is just computationally precise, okay. So you never have to leave a room for interpretations in algorithms, you have to be very precise with them, okay. Then yeah, the ultimate blueprint of this unit, the first of all, we understood what is computational thinking. So it is not coding, okay, it is the fundamental human architecture required before a single line of code is written, okay. Then decomposition, simply that is divide and conquer, okay. We just fragment massive systems into easily programmable and reusable PCs, okay. And abstraction, that is just builds efficiency by aggressively filtering out reality's noise to isolate the essential data, okay. So these are the things we studied video, okay. Then some knowledge checks are there, you have to just kind of understand, you have to solve them for yourselves, think about them. There are some sample questions, for example, okay. Define the term abstraction and state two benefits of decomposition. So think about this and answer it for yourself. Identify three essential features and two irrelevant features for a car journey model, okay. So if you're just creating a car journey model, just identify three essential things and two irrelevant things or features, okay, that are not needed for this model. And decompose atmospheric weather forecasting into three logical subtasks, okay. So if you want to just kind of create something like that, then decompose that, okay. So there can be just some exam questions. That's it, wish you all the best. If there is any kind of question, you may just ask that in comments. We will be more than happy to answer. Do not forget to like and subscribe our channel, and send these videos to your friends and introduce us to your teams. Wish you all the best, good luck and goodbye.